Question number 10 says, a 40-gram block of ice is cooled to negative 76 degrees Celsius and then added to 600 grams of water and a 80-gram copper calorimeter at a temperature of 27 degrees Celsius. Determine the final temperature of the system consisting of ice, water, and calorimeter. If not all the ice melts, determine how much ice is left. Remember that the ice must first warm to 0 degrees Celsius, melt, and then continue warming as water. The specific heat of ice is 0.5 calories per gram Celsius, or 2090 joules per kilogram Celsius. So here's what happens. We have this ice, it's at negative 76 degrees, and then we have some energy added to it in the form of heat that causes it to heat up to 0 degrees. And then at 0 degrees we have some more energy added to it that causes it to melt. And then we have more energy added to the melted water to warm up the melted water if all of the ice melts. Then we have this energy coming out of the copper, and then we have energy coming out of the water. And all of these changes net out to be 0. Now what do we don't know? We don't know, so this is the block of ice warming up, this is the block of ice melting. We don't know how much melts. Does all of this melt into water? And then if it does that water warm up? So we don't know a lot about this, we don't know a lot about this. Because we don't know either of these two, we can't figure out what the final temperature is to solve for these, to solve what the energy is on these two. Do these go all the way down to 0, or do they stop before 0? So these are the kind of questions that we don't know yet. The only thing we know for sure is Q1, that we know that the ice warms up to 0 degrees because it tells us that in the problem. And it really doesn't completely tell us that in the problem, but it is kind of implied. So what do? So I'm going to first set up the graph, or the chart that I always set up. And so since about 2 days after spring break, I lost my graphing calculator, still haven't found it. And so I already do most of these problems in Excel. I do most of my math in Excel. And so I figured why not set up my chart that I always set up using Excel instead of writing it down on a piece of paper. So what we got is the ice, it told us in the problem, was 0.04 kilograms. And we know that the specific heat of ice is 2090 joules per kilogram Kelvin. It tells us that, or we're going to assume just simply, and I'll explain this in a minute, we're going to assume first that this heats up to 0 degrees, this ice does, and that the initial temperature was negative 76, so the change of temperature is 76 degrees, and the L is NA for this problem. And then we're going to assume that all of this melts, and I'm going to explain these assumptions. Why am I assuming this here in a minute? And so 4 grams of it melts, and that's 333,000 joules per kilogram for the latent heat. Well, let me just go ahead and explain what my assumption is. So I know that if I have Q1 is my ice, so we'll say this is Q1, Q2, Q3, Q4, and Q5. We don't know if Q3 even exists, and we don't know. We don't even know if Q2 exists. We don't know that the ice even warms up to the point that it melts for sure. But we're going to assume if Q1 plus Q2, we're going to say that Q3 doesn't exist. This is going to equal negative Q4 and minus Q5. So negative Q4 minus Q5. And so if the ice just completely melts and that's it, then so these have the Q1 and the Q2 have heat being added Q4 and Q5 have heat being taken away, so these terms are going to be positive. So this has to be a positive term, and the negative of these losses have to be a positive term. And so what's going to happen is if this side is greater than this side, then we know that the ice didn't completely melt because we have more heat being added than what could have been possibly lost. If, however, this side is greater, we know that the ice did completely melt and some of the cold water was warmed up. So we're going to set it up like the ice completely melt and that was it. So the mass of the warm water was 0. Let me change the color back, 0.6 kilograms. The mass of the copper was 0.08 kilograms. Specific heat 4,186 and 387. The final temperature, since we're making this assumption, we're going to say 0 for both of those. The initial temperature is 27 on both of those, and so the change of temperature is negative 27 for both. And so L is NA on both of those. And so right now we're assuming none of the water warmed up. None of the melted ice warmed up in the bath of water as water. And so remember, this is a phase change. Q2 is a phase change, so you don't times it by a specific heat or a change of temperature. You just times the mass times the latent heat to get Q2. The other ones, it's mass times specific heat times change of temperature. And so what we end up getting if we add Q1 and Q2 is we get 19,000. Let me change 19,673.6 by our assumptions is equal to 68,649.1 by these assumptions. So what we know is that there was a lot more energy lost by the warm water and warm copper than was actually gained by the ice whenever it completely warmed up and melted. So we know that the ice needs to, the melted water at 0 degrees needs to start warming up some in order to come up to the energy equivalent that the warm water and copper lost. So actually what we're saying is this term right here does exist, and this is 0.04, so all of the ice melted. Now I don't know what everybody else's numbers are, and so maybe all of your ice didn't melt, but you will know that if this term is greater than this term. And if all of your ice did not melt, solving your equation will be much easier. But I will go over how to solve that after I go over how I had to solve mine, which was a massive pain in the neck. So now that all of the ice is melted, we have 0.04 grams of this cold water with a specific heat of 4,186 joules per kilogram Kelvin. It has an initial temperature of 0 degrees. And now we know that these final temperatures are wrong. We say we don't know what the final temperature was. We don't know what the final temperature here is. And therefore, we don't know what the change of temperature is. So we're going to solve for the change of temperature. And so this is NA. So how do we do that? Well, the only thing we know for sure is Q1. So Q1 we know that 0.004, and we know Q2. So Q1 and Q2 we know for sure. We know that 0.04 kilograms of ice completely warmed up to 0 degrees. And then we know that 0.04 grams of that ice completely melted. So that's the only, we know Q2 and Q1. We don't know Q3, Q4, and Q5. So here's how we have to set this up. Q1 plus Q2 plus Q3 plus Q4 plus Q5 equals 0, since it's in an isolated system. And so we already know Q1 and Q2, so we're going to isolate them onto the other side of the equation. So we get Q3 plus Q4 plus Q5 equals negative Q1 minus Q2. And since we already know what Q1 and Q2 are, we're not going to expand those. We're not going to try to give a definition for those. We're going to keep it as Q1 and Q2 for the entire equation. And then at the very end, we're going to substitute in for the numbers that we know equal Q1 and Q2. But on the other hand, Q3, Q4, and Q5 have to be substituted. So what was Q3? Q3 was the ice after it had melted. It was that 0.04 grams of cold water that needed to begin to heat up. And so this is I'm going to call it the mass of the ice, because the mass of the ice and the mass of this cold water are the same mass. So it's the mass of the ice times the specific heat of water times the final temperature of the system minus the initial temperature of the cold water. So we'll call it TIC. And then Q4, so this is equal to Q1. So Q4 is the mass of the hot water times the specific heat of water times the final temperature of the system minus the initial temperature of the hot water. So the initial temperature of the hot water and the initial temperature of the hot copper were the same. So this is equal to Q. So this was Q3, this is Q4. So the Q5 is the mass of copper times the specific heat of copper times the final temperature of the system minus the initial temperature of the hot water. Since the hot water and the copper were the same temperature, these two terms are the same. So it is equal to Q5. And so now we have to substitute in all of these equations for our Q values and solve for final temperature. let me move all this out of the way. I'm going to move this up. This is, well, I kind of need all of that there. So I'll just move all of that up that much, and we'll go ahead and write in the substitutions. So mass of ice times specific heat of water times the final temperature of the system minus the initial temperature of the ice water, or of the initial temperature. So one thing I want to point out, the initial temperature of the cold water was 0 because it started out as melted water at 0 degrees. So T final minus T initial C equals T final. It equals T final because T initial C is 0. So we can simplify this even further and just say the mass of the ice water times the mass of the water that came from ice times the specific heat of water times the final temperature. And this is plus the mass of hot water times the specific heat of water times T final of the system minus T initial hot. And then plus the mass of copper. So the mass of copper times the specific heat of copper times final of the system minus this same term. And I thought I could do this, but obviously I can't write small enough on this app, so I'm going to just go to my Note app, write this out, and then paste it back into here. So here you can see that the mass is the mass of the ice because the whole mass of the ice became water. So I'm saying that this is now the mass of the cold water, but it's the same as the mass of the ice, times the specific heat of water times the final temperature, because the initial temperature is 0, so the final minus initial is going to equal the final temperature, times the mass of the hot water times the specific heat of water times the final temperature of the system minus the initial temperature of the hot water. And since the initial temperature of the hot water and the initial temperature of the copper were the same, these terms are the exact same. So this is the mass of the copper times the specific heat of copper. Now this equals, like I said, negative Q1 minus Q2. So Q1 being the heating up of the ice to its melting point, Q2 being the phase change from solid to liquid. Now, the first thing that we're going to do is factor out. See that this term has identical. This is an identical part in each term, so I'm going to factor that out. So this term stayed the same, and this factored out. So we have the mass of the hot water times the specific heat of water plus the mass of the copper times the specific heat of copper. It's multiplied by the change of temperature. And so after that, we want to divide this so that we can free up the initial temperature to go to the other, so that we can add it to the other side. So we'll divide this first. And when we divide it, you got to remember this is a plus sign. So this is going to get divided under this, and it's going to get divided under this, but it's still going to free up our initial temperature. So we end up with the mass of the cold water times the specific heat of water times the final temperature divided by the mass of the hot water times the specific heat of water plus the mass of the copper times the specific heat of copper. And that's plus the change of temperature, and it's of course this term, it got divided by the same thing. So I want to point out something. This cannot cancel out because of this plus sign. So it's like bracketing this whole thing in parentheses when I have that plus there. And so behind here I've got the other part of this, and I'm going to push this all the way up and then blow this up a little bit. Okay, so after we divide it on both sides, like I said, I added the initial temperature of the hot water to the other side, and so that's the only thing that changed there. And then after that, so when we do that, on this side we have a term with final temperature in it, and both terms have final temperature in it, so I'm going to factor out the final temperature, and we end up with, so everything on this stayed the same except the final temperature is gone, plus 1. So if we multiplied this final temperature onto both terms, it would equal this. So we factored it out. Nothing changed over here. And then the final thing is, because the final temperature is multiplied by everything over here, if we divide this to this side, we can isolate the final temperature. And so that's all that's done, is to divide the other term to this side, and that is the final answer. So make sure you get your plus initial temperature of the hot on top of this expression. It's not a plus out here, so make sure it stays with the whole thing on the right hand side of your equation. And so that is your equation for the final temperature. Now, just so you remember what all of your terms are, I went ahead and took this picture. I plugged in everything that is known from the problem and from previous work prior to doing this equation. And so you got Q1 and you got Q2, so make sure you keep the negative sign on both of those whenever you put it in. So it's going to be minus 6353 and minus 13320. And then everything else you just substitute. So the mass of, so for example, the mass of the ice, 0.04, the specific heat of water, 4186, the mass of the hot water, 0.6, again 4186, mass of copper, 0.08, the specific heat of copper, 387, the initial temperature of the hot water was 27, and again, so everything is repeated down here, and you just got to plug it in, but you have to be careful. Make sure you plug it. I would do it again. I would do all of this in chunks. So I would do this part, and then I would do this part. I would write these numbers down, and then I would divide them, and then I would add this, and then I would write that number down, and then I would come down here and multiply these, then write that down, multiply and add these, write that down, then divide them, write that down, add 1 to it, and then finally take whatever you got up here and divide it by down here. If you don't have a good calculator, I would definitely do it one step at a time, like that. If you have a great calculator, or if you're using Microsoft Excel, it should be easy. The final answer, however, to this problem, if you got the same numbers I had, is the final, it's 18.07215 degrees Celsius. That's the final temperature, 18.07215 Celsius. If so I doubt anyone had the same numbers as me, but if you did, that's the answer. And there was 0 ice left. So the amount of ice was left, all of the ice melted. Now, if all of your ice did not melt, then that means you'd no longer have a Q3 term. What you end up with is Q1 plus Q2 plus Q4 plus Q5 equals 0. And so we already know what Q1 is, again, so we can subtract that over. We get Q2 plus Q4 plus Q5 equals negative Q1. Now, Q2, again, it's a phase change. So Q2 is the mass of this, and we'll put P, the mass of the phase change, times the latent heat. So ml. And then we know what the in this part, if we know that we have ice, we know that the final temperature is 0. So we know the change of temperature for Q4 and Q5 would be, they both started at 27, they went to 0, their change of temperature is negative 27. So we can easily calculate Q4 and Q5. So plus Q4 plus Q5 equals negative Q1. And so then we would just subtract over Q4 and Q5, but we would solve for what it is first. So it would be the warm water, the Q4, it was 0.6 kilograms times the specific heat of water, which is 4186, times the change of temperature, which is negative 27. And then Q5 was 0.08 kilograms of copper times 387 for the specific heat times negative 27. And so those are Q1 and Q4 and Q5. So to solve how much how much ice melted, let me see exactly how the question was asked. It's if not all the ice melts, determine how much ice is left. So how much ice is left? So right now we're figuring out how much melted. So we'll take that number and subtract it from our initial amount of ice. So we get that the mass of this phase change times the latent heat is equal to negative Q1 minus Q4 minus Q5. And we can divide all of our right-hand side of our equation by L. And we get the mass of the phase change is equal to negative Q1 minus Q4 minus Q5 divided by L. And that gives us the mass of the phase change. That's how much melted. So we take that answer, we subtract this from the initial amount of ice. So subtract that from the initial amount of ice, and you get so basically you would get that the initial amount of ice, which was 0.04 grams, is equal to, or the amount left. So let's say the initial amount minus negative Q1 minus Q4 minus Q5 over L is going to be equal to the amount of ice that's left. So the amount that's left. Now again, you don't need this part unless you experimented with me in the beginning and you found that you did indeed have some ice left, whereas I didn't. So it depends on the numbers that you're given by WebAssign.